Hello fellows and welcome back to another video of Epoxy channel. In this video series we will explore polysulfide epoxy systems, their unique chemistry, key properties and versatile application across various industries. This is the second video, so stay tuned and I hope you enjoy.
Liquid polysulfide polymers represent one of the oldest classes of specialty elastomers. Chemically, they are viscous liquids ranging from low to high molecular weight that are terminated with highly reactive thiol groups. These SHN groups make them ideal for cross-linking reactions in adhesives and sealants. Their structure provides a unique balance of properties. Polysulfides offer exceptional resistance to solvents, oils, and many aggressive chemicals. They retain flexibility even at very low temperatures, and they are highly resistant to degradation from ultraviolet light, ozone, and oxygen. In addition, they are excellent electrical insulators and are remarkably impermeable to gases and moisture, making them perfect for demanding sealing applications. They also show good adhesion to a variety of substrates and exhibit strong flex crack resistance over long service lives. These inherent material properties make liquid polysulfide polymers indispensable in a range of high-performance applications. They are commonly used as flexible joint sealants in construction and civil engineering, such as for roads, bridges, and runways. They serve as a primary sealant in insulating glass windows, where gas impermeability is critical. In aerospace, they are used to seal aircraft fuel tanks and fuselages due to their outstanding fuel resistance. Beyond sealants, polysulfide polymers are also used as modifiers in epoxy coating and adhesives, improving flexibility and impact resistance in these systems. In protecting coatings, particularly in thermoset fireproofing systems, they contribute toughness and environmental durability. In short, the versatility of liquid polysulfide polymers lies in their combination of chemical resilience, long-term flexibility, and excellent sealing capabilities under harsh environmental conditions. In this slide, we present comparative overview of various liquid polysulfide polymers from the Thioplast G series, developed and manufactured by Norion Functional Chemical GmbH, used in Greece, Germany. Norion is recognized globally as one of the leading producers of liquid polysulfides for demanding industrial applications. The products shown in the table are all short-chain aliphatic polymers containing two consecutive sulfur atoms in the main chain and terminated by reactive thiol groups. This basic structural motif allows for high flexibility, chemical resistance, and excellent reactivity during curing. One key component of the differentiation among these grades is viscosity, which ranges from approximately 1,000 to over 140,000 millipascal per second at 25 centigrade. Most of these products also have average molecular weight between 2,000 and 8,000 daltons, making them well suited for use in highly flexible sealants and coatings, particularly in industries like glass units, construction joints, aerospace sealants, and protective coatings. If you look at the table closely, you will notice the chain length, molecular weight, thiol content, and the degree of branching expressed as mole percent of 3-chloropropane TCP are all variables that have been fine-tuned across the product line. TCP is the branching or cross-linking agent used during synthesis, and it plays a major role in determining the final mechanical and processing properties of the cured sealant. For example, TCP levels range from 0 to 2 mole percent, influencing key performance characteristics such as pot life elongation at break, tensile strain, and Shorey hardness. Grades with lower molecular weight, such as Thioplast G4 and G44, are typically used as reactive diluents in multi-component sealant formulations. They are also commonly used as modifiers for epoxy resins, where they enhance flexibility and toughness without sacrificing chemical resistance. We will explore how these molecular and structural differences impact performance in the next few slides. This slide illustrates the synthetic pathway used to produce liquid polysulfide polymers, with a focus on their chemical building blocks and structural evolution during the reaction. The process begins with two main raw materials, bis-2-chloroethylformol, often called diformol, and sodium polysulfide, Na2SX. The sodium polysulfide used typically has an average sulfur rank between 2.4 and 2.6, meaning it contains a mix of di, 3, and longer polysulfide chains. These materials undergo a nucleophilic substitution polycondensation and aqueous dispersion. During this reaction, diformol acts as the organic dihalide while sodium polysulfide provides the nucleophilic sulfide ions. The result is a micromolecular polymer backbone containing alternating organic units and disulfide linkages or SS. Notably, chlorine atoms are completely displaced and are not part of the final polymer structure. To introduce branching and cross-linking site within the polymer, a three-functional monomer or 1,2,3,3-chloropropane or TCP is added in small amounts during polymerization. The presence of TCP promotes the formation of a three-dimensional network, leading to an initially high molecular weight product, around 300,000 Daltons, in the former a viscous latex. Once this highly branched high molecular weight polymer is formed, it must be reduced to a usable liquid form. This is done through chemical splitting using a reducing agent such as sodium dithionate and sodium sulfite. This reaction not only lowers the molecular weight and shortens the polymer chains, but also introduces thiol or SH end groups, which are crucial for later curing reactions. At the same time, any remaining high-rank polysulfide groups or RSX are converted to disulfide linkages. The final properties of the liquid polysulfide, such as viscosity, reactivity, and flexibility, can be tailored by adjusting the chain length, molecular weight, and branching density. This tunability allows formulators to develop specific grade optimized for various applications, from flexible sealants to chemically resistant coating and aerospace adhesives. This slide captures both the core synthetic chemistry and the molecular engineering strategy behind liquid polysulfides and giving us insight into how structure and synthesis control performance. Liquid polysulfides are medium to high viscosity polymers, typically exhibiting a light red-brownish hue. Their viscosity is directly influenced by the average molecular weight, which reflects the polymer chain lengths and degree of branching. These polymers remain flexible over a wide temperature range, from as low as -55 centigrades up to 140 centigrades in continuous service, and can tolerate intermittent exposure to temperature as high as 150 centigrades. Introducing up to 2 mole% of TCP allows for additional elasticity and flexibility. Notably, these polymers show no shrinkage during curing, making them ideal for high-precision sealing and bonding applications. Thanks to dynamic disulfide exchange reactions in the backbone, cured polysulfides exhibit stress relaxation and excellent mechanical resilience under cyclic loads. They also deliver exceptional chemical resistance, outperforming most commercially available elastomers when exposed to solvents, oils, fuels, and alkaline environments. Polysulfides can be cured via multiple mechanisms, including oxidative curing, isocyanide or NCO curing, and epoxy reactions. They can even undergo Michael adhesion with acrylate systems, offering broad formulation flexibility. In terms of durability, liquid polysulfides are extremely stable against UV light, ozone, and oxygen, key factors in long-term outdoor performance. Their self-healing capabilities, both in uncured and cured forms, rise from reversible disulfide exchange, which can repair minor surface damages over time. From a health and safety perspective, they require no special precautions, and importantly, they do not contain toxic tributylamine. Among all elastomer types, polysulfides exhibit one of the lowest gas and moisture vapor transmission rates, second only to butyl rubbers. Properly formulated systems also do not corrode metals. They are soluble in aromatic and halogenated solvents such as benzene, toluene, chloroform, and dichloroethane, as well as in plasticizers like phthalates, benzoates, and chlorinated paraffins, facilitating blending and processing. Their reactive terminal thiol groups allow curing at ambient temperature through oxidative pathways, resulting in rubber-like networks without volume loss. Cured polysulfides combine excellent elasticity with high resistance to UV, ozone, water, oil, fats, dilute acids, and alkalis. However, they are vulnerable to strong oxidating acids such as 50% sulfuric acid or 10% nitric acid, and can also be attacked by monosulfide solution in toluene, which degrades the S-S bonds in polymer chain. One of their most important features is their resistance to water-induced degradation. Their polymer backbone is hydrolysis resistant, making them ideal for long-term immersion applications like water reservoirs, sewage treatment plants, or fuel tank linings, where water resistance, even in the presence of fuel contaminants, is critical. Durability in wet environments also requires biological resistance. Pure polysulfides naturally resist a broad range of bacteria, including sulfur metabolizing species, reducing bio-deterioration. However, under formulated sealants with low liquid polysulfide content may undergo polymer reversion, leading to surface softening and degradation within 2 to 4 mm of depth. Finally, the optimal sealant composition for water or sewage applications contains more than 40% liquid polysulfide, manganese dioxide as the curative, and a chlorinated paraffin as the plasticizer. This combination provides the best balance of cure speed, flexibility, chemical resistance, and longevity in harsh aquatic environments. Curing of liquid polysulfides into high molecular weight elastomers is most commonly achieved by oxidizing the terminal thiol groups to form disulfide linkages. Theoretically, this transformation follows the simple reaction of 2-RSH to RSSR regardless of the oxidizing agent used. However, in practice, the choice of oxidant significantly influences the degree of cure and the final properties of the elastomer. The resulting network is based on disulfide crosslinks, which forms at ambient temperatures, ranging from a few minutes to several hours depending on the curative used. Because inorganic dioxides and peroxides are generally insoluble in liquid polysulfides. The curing process is often heterogeneous. Curatives with stronger oxidizing characteristics, such as permanganates or dichromates, tend to produce higher modulus sealants with enhanced thermal resistance. The most commonly used curing agents are oxygen donors, which include manganese 4 oxides, the industry standards inorganic peroxides such as calcium peroxides, zinc peroxides, and barium peroxides. Organic hydroperoxides like t-butyl hydroperoxides and cumin hydroperoxides, lead peroxides, permanganates, and dichromates are also used. Organic hydroperoxides, being highly reactive and soluble in liquid polysulfide matrix, can provide rapid and effective curing, resulting in high modulus elastomeric networks. However, this same reactivity means the curing process must be strictly controlled to avoid chain season and polymer evasion. Importantly, organic hydroperoxides that release acidic byproducts during decomposition should be avoided, as these can lead to long-term polymer degradation. Among all options, the most widely used adopted curative is especially activated manganese 4 oxide, valued for its reliability, safety, and performance balance. For specific performance needs, cumin hyperperoxide is ideal for formulating white, pourable sealants with high compression set resistance. T-butyl hydroperoxides offer curing with good UV resistance, forming stable polymer networks. Calcium peroxides and sodium perborates are popular choices for one component system and also serve in two component formulations, especially when white or color sealants are required. Finally, dichromates cured polysulfides offer superior resistance to swelling in hot water compared to those cured with manganese dioxides, making them highly suitable for challenging thermal and aqueous environments. Here is a summary of the curing agents we have already discussed. Manganese 4 dioxide is the most commonly used curing agent. It is favored when improved heat resistance and low toxicity are desired. Formulations cured with MnO2 also offer good UV resistance and stable adhesion even under prolonged weathering. With standard acceleration, such systems provide a working time of around 30 minutes, curing fully in approximately 8 hours at 23 centigrades and 50% relative humidity. Calcium peroxide, in contrast, requires moisture for activation, making it suitable for light-colored, one-part moisture curing systems. To ensure shelf life stability, barium oxide or BaO is often added as a dehydrating agent to absorb residual moisture. Moving into cumin hydroperoxide, this curing agent provides excellent compression set resistance. It is more commonly used in casting systems rather than adhesives or sealants due to its particular curing profile and performance characteristics. Sodium perborate is another effective curing agent. It enables the production of light-colored, non-staining sealants, usable in both one and two-part systems. These formulations deliver low modulus, high elasticity, and good resistance to water, UV exposure, and mold growth. Finally, inorganic chromates, though largely phased out today, were historically used in aircraft sealants to enhance corrosion and heat resistance. However, due to significant health concerns, their use is now being actively replaced by safer alternatives. The ease of oxidating thiol terminal groups explain why oxidative curing remains the dominant method for cross-linking liquid polysulfides. Importantly, the curing agent must be added in excess beyond the stoichiometric requirements for converting the available SH groups to ensure complete and reliable network formation. While curing generally occurs at room temperature, it can be significantly accelerated by heat, allowing formulation to tailor processing times as needed.
Now this is time to end this session, and I hope you enjoy. Stay tuned for the next slides on this fascinating topic. Thank you.